So my name is Payam. I support the developer infrastructure product team at Meta, where I spend really most of my time applying AI to the product development process. And I actually wasn't always a PM. I started off my career as an engineer at Microsoft, building developer tools, and then took a 15-year detour at Google before going back to developer tools at Meta about 2 years ago. And the reason I went back to developer tools is because I was blown away by everything that was happening in the AI-assisted coding space, and I wanted to join the party.
And my name is Pavel. I've worked on developer tools, productivity, and similar things for many years. Recently, and unsurprisingly, with an increasing focus on AI-assisted software engineering. So thanks for bearing with us. A lot of these slides might look a little familiar if you've been to the other talks. Everybody is thinking about our favorite topic, measuring developer productivity in the age of AI. Let me start by just acknowledging the excitement around this space, right? AI is a truly transformative thing. We all feel that. We don't know subjectively how to use it. We know objectively how to measure some of it, and we objectively don't know how to measure other parts of it. We'll try to tell you what we're doing as much as we can, not as much as we'd like, and we invite the questions and conversations. But just to level set a little bit, I don't know how much you all know about the specifics of the developer environment Meta. So we're going to talk a little bit about that, also about terminology, just so you're not confused. When we say diff and we mean PR, we're going to talk about the tools we have in the AI space, which try to cover the different aspects of the software engineering workflow, and then get to the meat of it, the measurements, the insights, the pretty graphs, if you will, numbers and trends, and some interesting findings that surprised us. So let's get going. What does our software development stack actually look like? So we were pretty proud of this slide, and I think at least 3 other talks had the same version or something very similar, right? The developer journey. As developers, we plan changes, we author changes, and that's where IDEs and other coding-related tools come into it. At Meta, certainly, and at most of your companies, I'm sure, every code change has to pass code review. The unit of review for us is called the diff. It's called the pull request in most other places, CL at Google, but if you hear us saying diff, that's what we mean. After review, usually there's some amount of back and forth. Eventually, the change is approved or stamped, and then it lands. That means it becomes part of the main branch that is ultimately deployed. At Meta, of course, we do feature-driven development or gatekeeper-driven development, so we roll out gradually. That's what we mean when we talk about release. We try it out on a few happy early users and hopefully then get to the whole population pretty quickly. The post-release phase is very important. It covers incidents, covers ongoing maintenance, and things like that. All of that is, of course, a bit of an oversimplification. Nothing survives contact with the enemy, and we support many different types of engineers. We have many different types of tasks. People work on mobile apps on the one hand, and on custom firmware for our ASICs and chips on the other ends, and everything in between as well. We support all the major platforms that you've heard of, some platforms you probably haven't heard of. And as a result, what our engineers actually use is a hodgepodge. Well, I don't want to say a hodgepodge, a carefully designed interlinked system of first-party solutions, but also third-party solutions, commercial and open source. So if we just go through the phases in order a little bit, for planning work, we have an in-house tool for issue tracking and project management. We also heavily rely on docs, of course, and on chat, and on posts, on internal fora, and meetings, and all those kinds of things. Code is primarily written in VS Code, or rather a fork of VS Code that is heavily customized for our environment. We have pockets of other IDEs, including Android Studio and Xcode for iOS and Android development. Not respectively, possibly vice versa. I don't know how I said it. Most engineers use special cloud environments that we call on-demands that spin up very quickly, but powerful but disposable cloud machines, which they can reserve at a moment's notice. But for certain workflows, you can also have a dedicated special box with hardware like a beefy GPU or extra memory or whatever you need. We use a monorepo. Well, actually, we use several monorepos for the development model, but for all the usual reasons that you usually hear. But the scale and the pace of change is really quite a bit of a challenge for those of us building systems. So everything is kind of built from the ground up. For source control, we have Sapling, which started as a fork of Mercurial and then became its own thing. For build systems, we have Buck 2 now, which gives us the incrementality and scalability that we need for our repo. The CI/CD system is heavily integrated with Buck and with Sapling to give us the parallel performance we need. And the code review tool is Fabricator. We've open sourced various versions of these tools, of course. You probably recognize them from the past. Also worth noting, we build languages and runtimes, right? So Hack is a language that is used outside Meta, but nowhere near as extensively as within. This is actually a challenge when we start talking about LLMs and what they're trained on. They haven't seen anywhere near enough Hack, so that's something we can think about. We also work with industry peers on advancing the state-of-the-art for compilers like Clang, language tooling, debuggers, GPU debugging, and so on. And all of that is before we start talking about AI. So what's changed in the past couple of years? Well, the journey has been probably similar to the rest of the industry, right? We introduced AI code completions some 3 years ago now. We launched a family of AI agents that cover the entire software development lifecycle. And I just want to briefly flash up some of them, mainly because we will slip and use their names, and I want you to recognize them when that happens, right? So for the plan, author, review phases, the primary agent we have is called DevMate. It's built into the IDEs that we support. It's available in the terminal. It's available in a web interface. It's similar to products like Cursor or Claude Code, and yet, there is other aspects to it, right? The biggest difference is how deeply it is integrated with our custom tooling, custom environments, dev servers, the monorepo, the services that we use, and how broadly adopted it is. The vast majority of engineers at Meta rely on DevMate in one way or another. Now, in building DevMate, we picked a few prevalent coding use cases and optimized the agent's performance specifically for those. We built specific tools to let it work with the systems it needs. We have some custom models trained on internal data. And the range is broad, right? Everything from front-end development, taking a Figma mock and turning it into working code, optimizing performance, testing, both generating tests and selecting tests, and everything in between as well. We have an autonomous version of DevMate that runs at scale. It modernizes our code base asynchronously. It fixes test failures. It performs migrations from one version of the API to another. It adds accessibility labels to UI components. It refactors code. Many other tasks that engineers don't enjoy doing. We were speaking about avoiding toil earlier today, and this is very much in that bucket. And of course, the increased pace of code evolution poses significant challenges for many downstream systems. So for example, the code review tool can become overwhelmed. Code review can become a bottleneck when there are many changes coming in generated very quickly. Agents can help, right, to some degree, not fully. But we use AI to boost efficiency for code review. We use AI to boost efficiency of testing and every other place in the developer lifecycle. But even beyond coding, we've built assistants and agents to help with feature exploration, data analysis, incident management, and much more. That last piece, the incident management piece, is particularly important because, of course, as I said, the pace of change accelerates. And the human proximity to code is diminished as we rely more and more on higher level interactions through DevMate. And so we need to get smarter about how to prevent and mitigate issues. I think it was mentioned already before in Karim's talk, but we have SevMate as an agent that helps you root cause what caused an incident, and can really shorten the downtime, the mean time to remediation for users. And finally, beyond code, beyond software engineering, we've deployed agents that help with general knowledge work because, of course, we know, again, Karim's talk and others have pointed this out, an engineer's time isn't just spent coding. In fact, not even the majority of an engineer's time is often spent coding. There are AI-generated meeting notes, AI-assisted calendaring, AI-assisted knowledge discovery and retrieval, lots of things that we try to do to reduce the overhead so that engineers can spend more time building. And all of this is underpinned by a very decentralized platform approach to building agents. Any team can build agents for their own specific needs. We do try to provide shared components to provide a baseline of easy extensibility, but we see specialized agents popping up every week, sometimes for a particular debugging task or to help with triage of user-reported issues in NRL, maybe closed-loop optimization for ranking algorithms, maybe performance optimization for large C++ binaries, and so on and so forth. As a matter of principle, we tend to use the best model for any particular task. Often that's a first-party model that we've trained on our internal data, our internal code. Sometimes it's a third-party model, right? We prioritize the productivity that developers will gain over dogmatically using one or the other. We have many specialized versions of Llama in particular, which are exposed to different parts of internal data and perform very well in, incident mitigation, generating hack code for auto-completions, which, as I mentioned before, is a challenge for general-purpose models, and other similar things. But, again, we use third-party models extensively. I'll hand over to Payam now to talk about how we measure developer productivity and what impact AI has been having.
All right, thanks, Pavel. So let's talk briefly about metrics, and then we'll see how AI is impacting those metrics. So our North Star, and many folks mentioned this today, is to accelerate feature velocity. And this includes the speed of prototyping and also the speed at which we go from code to production. And we look at a basket of metrics like everybody else. And one of the primary metrics we've been looking at over the years is this thing we call diffs per developer per month, or DDM. And we know this metric isn't perfect. Not all diffs are created equal. It could take days to write a single line code change. In some cases, it could take minutes. And the impact of that diff also varies significantly. Not all engineering work is captured by diffs. We have a lot of machine learning engineers at the company, and they have lower diff output. They spend more time in notebooks. And also, there are a lot of external factors that impact DDM. So every time we have a holiday, we see DDM go down. And so for these reasons, we don't really look at this metric at the individual team level. But when we look at it across the company, it's generally correlated with things we care about. So higher feature velocity, higher developer sentiment, and also higher team satisfaction scores, which we measure through this team dynamics survey that we do every 6 months. So really a good analogy for DDM is GDP, gross domestic product, or steps per day if you're monitoring your health. They're imperfect metrics, but they're correlated with the things that matter. And the same is really true for DDM. Now, having said that, we've started to look at a new metric that we call feature DDM. And we think this metric is better. We use an LLM to classify diffs into feature diffs and non-feature diffs. Feature diffs include things like adding new functionality to our apps, improving ads or feeds quality, building an internal tool, updating a schema, et cetera. And non-feature diffs are basically everything else. And that includes things like improving code quality, migrating code bases, fixing issues, et cetera. And the attempt is to basically assign value to a diff at a pretty high level. And we've seen that feature DDM is actually more correlated with business outcomes than classic DDM. And there are a bunch of other metrics we considered along the way. We looked at number of experiments shipped by each developer per month. The issue there is that not all teams run experiments, so the coverage was low. We also tried to develop more custom ROI metrics, but there are lots of teams at Meta that are in the 0 to 1 phase, and they don't have well-established and measurable business outcomes. So we hit the same coverage and consistency challenge. So feature DDM, it's a nascent metric. We like it so far, has good coverage, it's easy to measure, and is correlated with the things we care about. Now, we have those two things at the top level, DDM and feature DDM. AI doesn't really change those metrics. We still care about them. And then we have a bunch of input metrics that are these color things. You've seen different versions of this from us over the years. You've seen different versions of this from other speakers at this conference today. And we have velocity metrics that measure each step of the development lifecycle. We have quality metrics because quality is super important, especially in the age of AI. And then we have sentiment, which I personally spend a lot of time on because the open-ended feedback we get is super, super high signal. So that's a quick overview of the metrics. Now, let's talk about the new metrics we've introduced because of AI, because clearly we can never have enough metrics. And the key about these metrics is that we think they are drivers of DDM. And since all engineers at Meta use AI, we've moved past user adoption metrics, and we now look at the depth of engagement with AI. So how deeply is AI being used in the software development process is the thing that we really want to measure. So if you look at the simplified SDLC at the top of the slide, AI can contribute to each part of this journey to varying degrees. So what we wanted to measure is the penetration of AI and the degree to which AI is transforming every step individually, as well as across the entire lifecycle. So just to show how we did this, we're going to zoom into authoring. I'll just use this as an example. And it starts off with diff. Diff is the unit of work. And we look at 4 levels of AI assistance during authoring. And we got some inspiration from the levels of autonomous driving here. So at the top, we have diffs. Then we have the percent of diffs that were assisted by AI in any shape or form. Could be code completion, could be agents, you name it. Then we have those diffs that were assisted by agents, which we think is the next level of sophistication. Then we have agents that were authored entirely, diffs that were authored entirely by AI. And then we have diffs that were authored entirely by AI without any human involvement or guidance during the coding process. So it's a funnel. And we believe the future of coding is a lot more autonomous. So we look at all the losses at each step of the funnel, and that actually informs a lot of the roadmap. We also have goals for each step, and I look at the dashboard for this on a daily basis. So you can imagine doing this for kind of every step of the life cycle. How sophisticated and deep is the use of AI, and then also looking at it across. So how is AI actually improving these metrics? This was actually pretty complicated to attribute the amount of productivity gain that is coming from AI. And we wanted to do it pretty rigorously, so it took us a while. The traditional way we would have done this was to just run an A/B test. We launched DevMate, we have a holdout, half the company doesn't get it, the other half gets it, and you just see what the impact is. The problem with agentic coding is it actually takes a while for engineers to get really proficient at it. So when we ran that A/B test, we actually didn't get any meaningful results. So another way would have been to actually let DevMate get deployed throughout the company, let the engineers get really proficient at it, and then actually take it away from a certain portion of the engineering population. And that would have made Pavel and I deeply unpopular across the engineering teams because people were already getting value from DevMate. So we ended up using 2 different observational methods. First, we looked at multiple fixed cohort analyses, and then we also looked at a mixed effect modeling analyses. And then we triangulated and tried to see, do these analyses actually point to similar gains or not? And we tried to be as conservative as possible with the attribution of AI. So we are likely undercounting the impact of AI with what I'm about to show you. And then just one more slide on the methodology. We took the engineers we have and grouped them into 4 cohorts in this 2x2 matrix. So axis number 1 was high versus low DDM engineers, as measured a year ago, before we had agentic coding. And then axis number 2 is looking at AI usage, specifically agentic AI usage, as measured today. So that's how we took all of our engineers and grouped them into these cohorts. And the reason we split engineers this way is we wanted to control for a confounding factor where high DDM engineers might also be more prolific AI users. So we wanted to control a little bit for that. And then how do we define AI usage? We actually did this in two different ways. We looked at the percent of diffs that were agent assisted, which if you recall that funnel that I had, it was kind of like the third level in that funnel. And we also redid the entire analysis by looking at number of agentic conversations per coding hour. So we kind of went a little bit overboard, and we ignored the impact of all of the other AI tools we have. Code completion, AI code reviews, all this stuff that Pavel described. And the result is we saw a 6 to 12% increase in DDM for engineers who were kind of above average users of DevMate. And the effect was visible across junior engineers, senior engineers. And this is measuring output. It's not measuring coding velocity, which is just one driver of productivity. So you can see that you have the high DDM engineers at the top and the low DDM engineers at the bottom. And then we split them by AI usage. And you can see that the gap between those two lines was negligible before agentic coding. And then after we kind of rolled out DevMate, we actually started to see those lines starting to separate. So who knew? Agentic coding actually works. We also ran the mixed effect modeling analysis, where we controlled for developer demographics. We looked at product team, job level, primary language that they use, et cetera. And the results were all kind of in the same ballpark. So this is kind of the floor, we think, for agentic coding at a company like Meta, where we do have a lot of legacy code and a lot of brownfield projects. Now, we have some data that shows AI works. We all kind of intuitively knew that. But let's go one step deeper and look at how the lower level metrics change, because I think that's where things really become interesting. So there were 5 insights that we discovered. First is this J-curve phenomenon when you introduce agentic coding. It drops by around 15% in terms of coding velocity, then returns back to normal levels and continues improving. And we saw this trend both for senior and junior engineers. We released DevMate in waves. Each line is a wave, and you can see that every time we released it, there was a slowdown in coding velocity until things started to improve. Now, the obvious explanation is it takes a while for engineers to change the way they code. But we also noticed something else was happening. Engineers were spending less time IMing their colleagues, asking for information, searching for documents, and they were getting all of that in the coding flow. And it was actually pushing our coding time per diff metric upwards because engineers were spending more time in the IDE. Overall, that's a good thing because they were doing less context switching and spending less time on the non-coding stuff. But our traditional input metric of get coding time to go down per diff was moving in the opposite direction. So the takeaway here for us was sometimes metrics will look worse before they get better with AI. And also the connection between input and output metrics might actually change with AI. So that was an interesting insight for us. Second, we really wanted to see at what point does coding velocity really start to take off. And we looked at the percent of AI code in various buckets, 0 to 20, 20 to 40, et cetera. And we saw that really once AI is contributing kind of more than 60% of the code, we really see a meaningful improvement in velocity. And you can see that when AI is writing 100% of the code, the improvement is pretty dramatic, right? Like almost a 60% reduction in time spent coding per diff. So takeaway here is the big unlock really comes when agents are writing most of the code. And third, this one surprised us. We saw that senior engineers use AI more effectively than junior engineers, despite the fact that junior engineers are more prolific users of AI tools. So we know that junior engineers generally adopt technology faster. All of our internal data shows that. But when you look at the percent of AI code that is generated by AI, the average diff by a senior engineer just has more AI code. And so it seems that senior engineers are better at prompting and guiding the AI to get a task done. And perhaps that's because senior engineers like Pavel are used to giving very specific instructions to junior engineers. And now they're just giving it to the AI. And of course, the process for junior engineers involves more exploration. And so this insight really showed us that technical foundation, technical experience, and the ability to communicate intent clearly, both of those things matter a lot. And this is especially true for junior engineers who often ask us, how much time should I invest learning the technical foundations of how software development works at Meta versus just jumping into DevMate and being productive? And we still believe that technical foundations matter based on this data. Fourth insight, engineers' perception of productivity actually matches the observational data here. And this is important because I think during a hype cycle, we tend to hear striking anecdotes, right, of really impressive wins among a handful of early adopters. But how widely are those gains actually distributed? And so we have this biannual DevX survey. The results just came out last week. And we see actually that 96% of engineers, the blue and the green parts of this chart here, feel that AI is actually helping them. And that on average, those who report the largest gains in that green chunk there also showed the largest improvement in diff output. So this kind of increases our confidence in both of these measures. And then lastly, on code quality, this has been a puzzle for us. How is AI impacting code quality? With the proliferation of AI code, do we see any impact? And we've done a bunch of studies on this internally, and the impact is pretty inconclusive. However, when we look at lower complexity tasks, and these are generally either tasks that are fully automated by deterministic bots, or where 100% of the code is written by AI, which is the blue line, we see that AI diffs have a lower risk score, which is that risk score that Nachi was talking about this morning, than deterministic bots. For higher complexity data, the data is inconclusive. So how do we get some clarity? Well, this is where the stuff that Pavel is going to talk about next comes into play. To understand the impact of AI on quality, we need to understand at a granular level where AI is changing our code base, at the character level, and how these changes are impacting quality over the long run. So I'll hand it over to Pavel, and he'll kind of show us all the telemetry that we built to enable these metrics.
Yeah, thanks. So this is an interesting one. This is the maybe more unusual bit of this talk. I haven't seen something like this in the other talks so far. But I remember a year ago, Payam and I were having very heated discussions about what to measure, how to measure it. % AI code. You may remember certain CEOs in earnings calls mentioned how much of their code was written by AI, or maybe not. Other CEOs went on podcasts or in fireside chats and said similar things. And it was never clear what that means. It was never clear to me as an engineer how you could measure that and stand behind the metric. And if you were in the fireside chat this morning, Brian very eloquently described how looking at AI-generated lines of code doesn't help. It's not a meaningful thing. It's not something you should optimize for. So what am I even talking about? Well, it turns out that lines are definitely the wrong unit. It's not useful. It's too granular. It's meaningless. But if you make it precise, you can do some interesting things. So the core question that Payam pushed me to try to answer, and eventually I relented, was which characters were written by AI and how, right? Not lines, not files, not diffs, characters. And how? Not just by AI, by this specific request, by this specific agentic trajectory, by this specific tool, by this model. That level of visibility gives us a huge array of options, not necessarily just to define a top-line metric, which of course you can, right? We mentioned % AI code in passing before. But you can do all sorts of other interesting things. You can reason about the quality of the output. Is AI code actually better or worse by whatever objective measure you want to throw at it? Is it harder or easier to maintain? Is it more commonly or less commonly reworked, re-implemented, revisited? And then we can reason about what models perform better, what tools perform better, what training gives us better outcomes because we have this really fine-grained visibility to the LLM request level of what lands in the code base after that training happens. We spend a lot of our time improving prompts, improving context, and so we can really see what tweaks actually matter, what improves the output. There's also interesting product design things you can do, right? Imagine that in code review, when you have a mostly AI-generated diff, next to the patch itself, you could show, this is the prompt that led to this. This is a link to the trajectory that the LLM took. You can see what the LLM did to validate it. You can both understand the intent of the change and build your confidence that it's actually done something reasonable. But that's hard. It's very hard. So, of course, we approximate, but I want to give you a flavor for what sort of things we do track. And so I have here some screen recordings of me working in VS Code. I don't want you to focus on the code too much. It's deliberately, too small for that. But I've also enabled decorations in the code that show what we're collecting, what we're tracking. So these blue spans that you can see, those are identified as AI characters. And again, remember, there is more to it than just AI or not. We're remembering which request it is and various other metadata. The yellow spans are things that I typed, the human typed. So the slide is meant to illustrate some of the complexities involved with this. Again, don't focus on the precise details of the code, just observe that I'm coding fairly naturally. And I've got it, the important thing there are several important things I want to highlight, right? So firstly, the majority of the code is neither yellow nor blue. That was an interesting insight. We don't actually care too much at the point where you're editing the code what the previous state of it was. We care about the new characters, the new work that you do. When we reason about %AI code at land time, we're going to reason about the new code, not the pre-existing code. If you want to look at the whole repo, you can, right? But we focus on changes. Another subtlety is over here. You can see I'm asking DevMate to add error handling to this method. And it wraps it in a try-catch block, and it indents it. And if you look at the diff in Git or in Sapling, it will show every single line as new, as modified. But that doesn't mean that every single line was generated by AI, right? It was pre-existing. So you can see we actually minimize the change, and the blue highlighting only applies to the indentation characters and to the try-except code. There's one more interesting interaction I want to show you here, which is, so I'm asking DevMate to rename a variable for me. And here it's running in an agentic mode where it'll propose a change and ask me to approve it or reject it. And you can see in the diff markup that the blue boxes highlighting characters as AI are there. But if I reject the change, the variable becomes yellow. So I undid the AI's change. And suddenly some code that hadn't changed became human-generated because I took an action as a human. I corrected or course-corrected for the AI. Now, whether that's the behavior you want, you can reason about, but it's something you have to think about. What does it mean when AI regenerates code that was there, like we saw in the add exception handling example, or when I, as a human, undo AI code? So, again, all of this is just the flavor for what we're thinking about. There's one key insight here, which is that this has to live in the IDE. It has to be in the editor, because all of these intermediate states are only in memory. You don't save after every edit, especially if you're using, code completion, if you're typing away. You can't work at the granularity of disk changes. You have to work on the IDE's representation. So you have to be inline in the IDE. So that's fun. We build stuff into the IDE that tracks what AI does, what edits happen on top of it, what rework happens on top of it. But then at some point, we need to persist it. We need to connect it to what we actually care about, which is what AI code is landing. And so here we'll talk a little bit about source control and the complexities involved. If you think of the green line of commits at the top here as our landed history, the things that have gone through code review and have been accepted and merged and potentially deployed, you can see it's linear. There's a reason for that. Whenever we land a diff, we actually rebase it on top of the history. We enforce a linear progression. But the user never actually commits to that green line of commits. Instead, they create commits on the side, typically branching off some suitable point. And so these dashed lines, they represent the familiar parent-commit relationship, parent-child commit relationship in source control. But the human-created commits are going to be the blue ones and the orange ones. And in fact, there's many different operations that create commits. So you have actual commits operations or SL commit, but you can also amend or in Git terminology, edit or rebase. You can merge or fold. You can do various transformations on the changes after they have been made, which is complicated for our tracking because, well, those changes might actually happen on a different machine. They might be done by a different person. It's hard to connect the dots. And remember, what we capture in the IDE, the metadata about which spans are AI generated and what requests generated them, they're attached to those commits. So I've illustrated them with sparkles. Now, we don't care about those. This commit a priori provides no business value. It provides business value when it reaches the green line, when it lands. So how do we get there? Well, it turns out that Sapling, our version control system, actually tracks enough metadata for us to work this out. This is not very common. I don't think Git tracks enough metadata, for example. But in Sapling, you can tell what a commit's earlier versions were. So I've illustrated that with the dotted lines here, right? So B1 was rebased into D1. But Sapling remembers that. D1 is a new commit, but conceptually it came from B1. And similarly, we folded A2 and B2 into this combined commit, and so on. Whenever a diff lands, a diff corresponds to a commit. At that point in time, the landing process itself rebases it into another fresh commit at the end of the line. And so now we can track it. You can see the sparkles in brackets appearing. Basically, we propagate along these mutation edges what changes to the AI spans were made in the predecessor commit. And that can be arbitrarily complicated, by the way. There's many corner cases. So I've got just one here where this commit ends up accumulating data from two other commits, and suddenly it has information about two potentially very different sessions on different machines about what AI generated that code. And then when it lands, we know that those sessions contributed to that G commit up there. And when it lands, we can count and compute and measure and track and visualize all of these spans. Now, both of these things, as I said, the in-IDE tracking and the SCM propagation, they require additional instrumentation to be captured in real time. Once the operation's happened, it's gone. It's impossible to backfill. You can't recover it after the fact. So actually, we're working with Anthropic and Enisphere on making sure that they have granular enough telemetry to integrate their tools into this kind of system where we want to see what did Cursor generate, what did Claude Code generate, and how does that differ from what DevMate did. We expect to be sharing more technical details on this in the coming months because we think it's a really cool application of data-driven analysis. And we'd love to see the industry agree on what we mean when we say there are 30% AI code in our code base. Very briefly, I don't want to keep you from the happy hour for too long, but I also want to talk about non-coding AI assistance. What I showed you so far, tracking AI changes to land, is well and good, but we use AI for all sorts of things, not just for writing code. Sometimes engineers ask questions about the code. Sometimes they plan changes. Sometimes they use AI just to unblock themselves and accelerate. And we ideally want to capture that as well, at least to be able to reason about it in the funnel that Payam showed with the different levels of autonomy of diff. And so we actually built a system for capturing traces of developer activity and connecting them to tool use, in particular to LLM, request responses. Karim talked about other applications of that system this morning. And last year at DPE, we actually spoke about diff authoring time, which lets us connect specific time slices with specific diffs that land. And this is how we connect non-coding AI assistance to diffs. if a user asks our agent a question, even if it doesn't generate any code, but that happens in a time slice associated with a diff, that's an AI-assisted diff. Of course, once we have that system, we can use it for all sorts of other things, right? We have great insights into developer activity. We can optimize time and dark matter. We can also explore ways of improving our own models through continuous pre-training or reinforcement learning, supervised fine-tuning, and so on. Anyway, I want to hand back to Payam to talk about a few ways in which we have been making the transition to a more AI-native workforce.
All right, thank you, Pavel. We're almost done. Many of us are making the transition to AI-native software development. And so we thought we'd just close with like 5 things that we've learned along the way as we've been trying to make the transition at Meta. Sometimes lessons from big tech companies don't always apply to other companies, but I tried to select a few that I think are broadly applicable. So first, I think many companies are trying to get their engineers and employees to use AI. We've heard a lot about AI mandates, and they can definitely help accelerate adoption. I'm actually curious, how many companies here have AI use mandates? Maybe 20% or so? Personally, I think a better approach is to create light bulb moments. At Meta, we have, every day I hear about really amazing stories of engineers using AI in ways that are pretty incredible. 2 weeks ago, we heard of an engineer who built a human labeling tool over the course of a couple of days that in many ways was better than the tool that a team had built over the course of like 6 to 7 months. There was an engineer last week who reduced the size of the Facebook app using a particular code optimization technique. And the app size reduction was more than all of the work that we had done in H1 using that particular technique. So when engineers see these case studies, they want in. And so, we've heard this from others, but I would just like to re-emphasize, find the engineers that are living in the future, amplify them, and then just let their case studies kind of galvanize everyone else in the company. Second, learning is, we know engineers love speed, both in terms of getting their hands on the latest tools and models, but also when it comes to inference latency. So my advice here would be to just try out all the tools and models out there, see what works, deploy them really quickly. I think speed of deployment is more important than how carefully planned and how smooth the deployment is. And inference latency is a really big deal. We've seen, especially for synchronous coding with AI, sometimes accessing models directly from the model providers gives you better latency. Sometimes it's better if you go to the superscalers. So you may find it worthwhile to pay premium inference for synchronous tasks and then use the cheaper, higher latency inference for asynchronous tasks that you may be running kind of at night. Third, others have said this, but again, worth highlighting again, I think agents without access to sufficient context and all of the tools are hobbled. And so beyond just using MCP to wire everything up, I think it's important to think about access controls for these agents. Do they impersonate the person behind the keyboard? Do they just have the same permissions as you do when you're using the agent? Do they perhaps have limits as to what they can do? Or do they actually have more privileges than the human behind the keyboard? These are all, I think, important questions to answer, and there's no right or wrong here. And we've also seen how important it is to actually do cleanup work on wikis and documentation so that the AI is actually accessing accurate information. And of course, you can use AI to do all that cleanup work as well. Fourth, I think evals are certainly a very critical spec, especially if you have a lot of custom workflows and processes in your company. Once you create these golden task and solution pairs and set up the eval environment, engineers can do a lot of the hill climbing against those evals through all the standard techniques, whether it's context engineering, stringing together multiple models, improving the agent harness, doing post-training, and so on. So I think the key here is, how do you set up the right incentives to write evals and then do the hill climbing so that agents become better at the company. And we've seen that engineers are incredibly resourceful. If the incentives are right, they're going to build agents that just continue to climb the eval leaderboards. And then lastly, coding is kind of becoming a commodity. almost like a tactic as it becomes cheaper and more ephemeral. We've seen engineers vibe code tools and features before the review is even scheduled or the alignment meeting is scheduled. And so it's like not only more efficient to do prototyping, but it's also just a lot more fun to be in a review where you're looking at the live thing and you can play with it instead of having mocks or documents to review. And I think one way to encourage this behavior is to get leadership to adopt the same mentality. So have the senior folks in the organization actually play around, do some vibe coding, prototype, write documents with AI. Grab the VP in your organization and actually sit down with them and have them vibe code and then show that video to the rest of the company. So those are a few things that we've been trying to do internally to make the transition to AI native development. We're learning a lot. We're making lots of mistakes along the way. And we hope that some of these insights might be useful for all of you. So with that, we're happy to take any questions.